Announcements?
Yeah, so thanks everyone for coming. For those large numbers we have here, I'll turn the camera around to show you, but it's too big to fit actually in the screen. All right, now. So thanks for being willing to talk on such a short notice. This is Tom. He's talked before. We'll probably talk again. Just a couple quick announcements. For those who haven't never done it before, Hacktoberfest just started this month. So DigitalOcean and GitHub pair up together. If you submit 4 PRs to open source, or open source is a very wide term, it's essentially any publicly accessible GitHub repo, you get t-shirts. So this is 2 years ago. You get these awesome t-shirts for free. They just sent it to you. This was last year's. This year's actually looks way cooler, and you get stickers. So, and bragging rights that you contributed to open source. My first year, I just started on Python. I had no idea what I was doing, never contributed to open source. So I did grammar corrections on Django's documentation. All right, I mean, it gets you there, gets you started, right? I think every year most of my coworkers contribute. I have some little word games I have for my kids, and every year I get a whole pile of pull requests from coworkers adding new vocabulary words, which, I mean, like, let's be a little higher sided than that, right? They don't have to be merged, they don't have to be accepted, you just have to submit them during the month of October. So if you just do a Google search for Hacktoberfest, DigitalOcean is all over their main page, GitHub's main page. If you don't know what to contribute to, GitHub has a whole Hacktoberfest page of projects, people asking for help, all the way, they're ranked from like, can you read, up to like, do you know how to do like kernel maintenance, right? So a whole range of projects.
Canvas also has a bunch of issues and labels by difficulty and all that stuff.
So a bunch of stuff out there. Just get you involved, excited about doing open source. And free swag. Right? I think David had something he wanted to share.
Yeah, actually, I'll just pass this around. There's an event this coming Saturday. I can't pronounce it. It's a long acronym here, but it's a get-together. It's going to be a gravitate, and it's to learn new programming languages, or to learn a new programming language, or to teach someone a programming language. So the idea is to show up with either knowing some languages or having a language that you want to learn about, and then
I'm not sure where the focal point is.
I'm not involved in organizing this at all. Somebody asked me to.
Somewhere there's the focal point. I'm not sure.
Yeah. What time is it actually?
It's at noon.
Yeah, noon to 4 p.m.
And there's a registration there of $6. I don't know if you could just show up.
Gravitate Ballard Junction.
Yes, I failed to mention that. Sorry. Gravitate Ballard.
Cool. I think we'll get started then. Does everyone have the materials now? Hopefully. You got them? Okay. And can you hear me all the way in the back? Hopefully. Good enough? Okay. I'll try and talk loudly. So, these are materials. We're doing this tutorial from SciPy that Andreas Muller and Alexander Gamfort, I think, or yeah, something like that, gave at SciPy 2017 this year. It's an 8-hour tutorial, so we'll do the first little bit, pick out bits and pieces that are interesting, cover a bit of background as well. If you have Conda installed, you can run Conda. I'm in the repository right now, so you can run Conda env create, and that'll pull down all the dependencies that you need. If you don't have Conda, I don't know if they included the requirements that you see it looks like they did, so might be able to pip install that and get everything going. Otherwise, activate your environment. I think create something called SciPy tutorial. Tutorial SciKit Learn. you're not familiar with Conda, it's a package manager, kind of like pip, but does other things too, including environments. It's made by Anaconda, my employer. And then once you've got the environment active, start up the notebook with Jupyter Notebook. So Jupyter Notebook is the command you want to run. I'd encourage you to be working along, just because it'll be a long hour and a half. I figure we'll go for like an hour and a half, and see where we're at. Everyone able to get the notebook server started up? Who here's not used the Jupyter Notebook before? Okay. Who here has used the Jupyter Notebook? Good deal. So we'll talk about that in the second notebook, actually. A bit about that very briefly, but it's like a REPL. You have a Python kernel in the background that's actually taking your input, giving you output, and then packaged up into a web application. So, okay, so machine learning. Most of this I'm going to skip and just like refer back to David's talk, so you can check that out. I think that's on the channel if you want. But yeah, the basic idea behind machine learning is you've got these, you want to make some decisions somehow, but you don't want to be like, hard coding, programming those decisions in. You're going to take some data and some outcome that you're interested in, and then learn some rules somehow to make the decisions for you automatically. The way it's typically talked about, at least inside SciKit Learn, is that you've got a training steps where you have some training data. We'll talk about what that is, some labels maybe. You fit a model to the data, so that's a training step, and then you go out and then you generalize to previously unseen data. You might have a test data set, which we'll talk about in the third notebook, I think, and you evaluate your performance on that. So those are the two main things, is you have a data set, an X and a Y potentially, you fit a model to that, and then you generalize to previously unseen data. That's the prediction step. Okay, and I think we're gonna, so mathematically, David talked about this, but the data, there's SciKit Learn calls it X and Y, so X is like the actual stuff that you observed about it, and Y is the thing that you're predicting. X is going to be a matrix where each row is an observation and each column is a feature. So the canonical example is some species of flowers. I think like Fisher, like the statistician Fisher is the guy that collected this data, so it's used everywhere, but he got some 150 different samples of these species of iris and measured 4 attributes about each one, the petal length and width and the sepal length and width. And that's like the data set. So each row here is an individual flower that he observed, and then you have like the petal length and the sepal length and the petal width and the sepal width. Those would be your 4 different features. So that's like the layout mathematically, and we'll talk about the programming side in a bit. Last little bit here is supervised. David talked about the split between supervised and unsupervised. We're just going to talk about supervised here. So supervised learning is when you have an outcome that you're trying to predict. So these are things like regression and classification are the 2 big ones, and that contrasts with unsupervised learning, which is like clustering, basically. There's no correct answer, but you're still trying to learn something about some data set. In the case of like clustering, like if you're picking out the topics for a bunch of news articles, there's not like a correct answer for any given article necessarily, and you might want to be clustering these different articles together into broad topics, roughly speaking. Okay, so within supervised learning, there's classification and regression. Those are the big ones. Classification is when you're predicting a discrete valued output. So like, is this spam or not? Or like the digits example that David talked about, predicting, taking a handwritten digit and predicting which one it is. There's 9, 10 digits that you could be predicting. So those are those are examples of classification. And the regression is when you're predicting a continuous value, like the price of something. Okay, so that's that. Nice little diagram here. Like I said, we're not going to talk about unsupervised learning at all. Okay, second notebook. A if you want to get that open. So yeah, this is talking about Jupyter Notebook. It's like I said, you can execute code and get the outputs in the notebook itself. Really, the only one you need to know is Shift-Enter will execute a cell. So when you run it, you can see that all this code runs, and then the output, which is this print here, is what actually gets run. And then the output is returned to however the notebook application decides to capture it. Okay. First data structure, or the one data structure we'll talk about, is the NumPy array. This is what SciKit Learn uses for the most part for storing, for basically fitting. It's what you'll use to. It's the type of data that you'll pass into SciKit Learn. And it'll take it from there. So NumPy array is a data container like a list or a dictionary or whatever, but it's been optimized for storing dense, homogeneous, mostly numeric values. So you can stick whatever you want in there, but for the most part, you're going to be wanting to stick with integers, floats, and that sort of thing. Indexing, I think we'll mostly skip through this, but it behaves basically how you would expect. The only thing is it's to get rows, it biases towards selecting rows first. So the second one is going to select the row one instead of the column one. If you want to get a column, then you can use this colon syntax to select every row and then the first column from the second dimension. Any questions on that? I don't think we're going to be using indexing too much. For the most part, we'll just have the arrays. Okay, and then transposing, we won't really need that linspace. We don't need this kind of like range, but we won't be using it. Don't need that either. Random numbers we'll skip over as well. Fantasy indexing we'll skip over, and sparse matrices we'll skip as well. I think we'll skip matplotlib too. So sparse matrices, they're a way of storing data that has a bunch of zeros. This is pretty common in certain domains in machine learning, like if you have if you're trying to represent like an article, a text article, as an array of data, one way of doing that is to just like have an array with every alphabet letter, every word in the dictionary, and then the count of the times each word occurs. And so since most articles don't have most words, most of the elements will be zeros. SciPy sparse matrices can store those in a memory-efficient way, but we'll be ignoring that. And then matplotlib's a plotting library, which we'll just use, and you don't have to really worry about for now. Okay. Last little setup preliminary notebook here is representing data. So, like I said, for the most part, using NumPy arrays. And the shape is always going to be n samples, which is like your number of observations. So in the iris example, there's 150 different flowers by n features. So this is the shape of the array. It's going to have n samples by n features. So in the iris example, it's the four measurements that Fisher took. Okay. Going back to this iris example again, I think we already talked about this for the most part. So, question: what would the n samples refer to? It's the 150 samples that he took from the field, and then the n features would be the four things: the widths and the lengths, that sort of thing. Okay. So for SciKit Learn, SciKit Learn is like really focused on the algorithms and leaves all of like the or most of the data processing stuff to other libraries like NumPy and Pandas. So everything we'll be seeing here is going to have like super clean data sets that you won't have to manipulate in any way, really. If you do need that, use Pandas. And, talk to me if you have any questions about that. But for the most part, we're going to assume that we have a nice, clean data set that's already in the proper format to be passed to SciKit Learn. Okay, so for the iris data sets, like I said, there's these four features, so lengths and widths in centimeters, so these will be floats. And then the target, in this case, is the species that you want to predict. So there's three possible species. We have three possible outcomes, so 0, 1, or 2. So is this an example of classification or regression? What do you think? Classification, yeah. Okay. So SciKit Learn bundles a few data sets. We can import them here and then load it here. So the return value here is a bunch object. It's like a dotted dictionary. We won't use it that often, but the important thing is it stores the X data, so like the actual, the 150 observations by the 450. It's a one-dimensional array, so there's no second dimension there. This is pretty common for when you're predicting things, and then we can print out the outputs here, so you can see it's kind of been sorted already. Okay, we can do a bit more here. I think we'll skip most of this actually. I can talk through it real quickly. Just kind of like exploring the data set a bit, visualizing it in 2 dimensions. So getting a histogram of the width. So we've selected the, where did we select the? Somewhere in here, X index 3. So this is selecting the fourth item out of the X array. So this is grabbing X of all the rows and then 3 iris dots. Anytime I say X, I mean the exogenous, the predictor. So grabbing this this column of sepal petal widths, and then making a histogram of them. And you can kind of see that there's some differences here, right? So this is like what you're looking for when you're trying to get good machine learning features. You want some sort of variation in the predictors to be able to predict the output. Like if they were all overlapping, then it wouldn't be a very good predictor because there's no like discriminatory information in that variable. But this one's pretty good. So typically for the larger petal widths, we'll be predicting Virginica. For the smaller ones, we'll be predicting Setosa. But yeah, this is just kind of exploring things. And I think we'll skip the rest of that and get into the first real notebook. Digits data, if you wanted to see the one that David talked about last time. Okay, so 4th notebook. Now we can actually get into things for real. Any questions so far? I should say, just ask if you have any. I know I'm going fast. It's all set up, so hopefully we're good. So far we have NumPy arrays for storing the data, typically numerical data. X is going to be our, so here, X is going to be our, the stuff, the features that we're going to use to predict the Y, which can be either discrete valued or continuous. That'll determine whether we're doing classification or regression. Last little bit of setup here is, typical thing in machine learning is you want to avoid something called overfitting. We'll talk about it later. And I think, David, did you talk about overfitting generalization? Yeah. Okay. So it's you can get into situations where your model is like too tightly attuned to your training, like to weird noise in your training data set, and then it ends up not being a good model. It ends up predicting poorly because it basically memorized your training data set and memorized all its weird idiosyncrasies. So when you're doing these, you'll typically split your data that you have at hand into a training set and a test set. And the training set is what you'll use to fit the model, and then the test set is what you'll use to evaluate the performance. So going back to the first notebook here, we have these 2 kind of steps here. We'll be training on fitting the model on the training data, and then evaluating it on the test data set. Okay, so, and then I think I'm going to, we'll go a bit more. So we're still working with the iris data set. I'll talk about this Neighbors Classifier in just a second, but actually one second. We're going to go partway through this notebook. We're going to go up here. Right. Okay. So we have this classifier, and I'll talk about what that classifier is in just a minute. And then we're predicting this Y, which is the discrete valued output. One thing, if we just like selected, say, if the training data set, so if we did like train X is going to equal to like X of the first 100, say, and then train Y is going to be Y of the first 100, what might be a problem with this?
You won't have all the species.
Say again?
You won't have all the species.
Right, yeah, so this data set has been sorted somehow. by the outcome, the y. And so if you go to fit the model to this data set, this train x, train y, you're going to be in trouble because you'll never predict 2 because it doesn't know about 2. So, and you'd get like 0% basically because everything is 2 on the back half. So typically you'll want to like shuffle your data set before doing the train test split. SciKit Learn has a bunch of utility functions to help with this. In this case, we'll use train test split, which you give an x and a y. Actually, you give any number of iterables, take star args, and then the keyword arguments are going to be the ratio or the number. You can pass in integer values here as well, and it'll shuffle and split your data set for you. So this would be a good training data set to use. And then last little bit is this stratified split. This can be good when you're doing, what do I not have NumPy? Did I not? I don't think I ran the very first cell. When you're doing classification, it can be, you can run into situations where you have imbalanced number of classes, and you want to be careful that your training data, the proportion of the classes match up between the training and the test data set. So that's what stratified split will do. So like in this case, the training data set happens to overrepresent the second item here, the second outcome. With stratified y here, this is the same thing. It's going to ensure that all of the class labels gets the same count. So there's like minor little things that can creep in, and we'll talk about like how you determine that your basically all of these little things can cause you to be overconfident about how well your model is performing. So later on we'll talk about how to measure that. Okay, before we execute this cell, I'm actually going to jump over to the 5th notebook, if you would come along with me. So we're going to go into the Supervised Learning classification, talk a bit about the SciKit Learn API, and then we'll jump back and finish off this notebook. And then I think we have an exercise at the end finally. Sorry about the long delay. Okay, so Supervised Learning. I think we're first of all going to start off by visualizing some data here. So we have just a fake data set. This make blob is going to make some circular stuff. So X is again, NumPy array, which you can see here it floats. Y is an outcomes, discrete valued outcome. So we're going to be doing classification. And with the two-dimensional data set, we can actually plot it and see what things look like. So we use this matplotlib scatter function to make a scatter plot, and you can kind of see that if you're just kind of doing this by hand and you wanted to do like draw like a line to separate these two, you would draw it like somewhere around here to separate the zeros from the ones. Anything above the line would be a 0, anything below the line would be a 1. So kind of the idea behind machine learning is like figuring out what is the intercept and what is the slope of that line. Rather than you determining that by hand, machine learning is doing that for you. So that's like all machine learning is. It's pretty boring. Okay. So since we talked about train test split, we're going to be good about doing that. We'll use stratify y since we're doing classification here. And we've seen this diagram already. And we're going to use logistic regression. I don't know if David talked about this or not. He talked about logistic regression, but it's actually classification, even though it says regression in the name, just to confuse you. So the way SciKit Learn works is all of the estimator objects, you import an estimator and then you instantiate it. Each of these takes like a whole bunch of parameters that control various things and how the fitting is done. So I'm pretty sure David talked about regularization. So this would control the regularization of the coefficients, things like the loss function I know David talked about, whether or not you're going to add an intercept, which deep learning calls bias, things like that, things that will control the fit. The solver, he talked about that as well, with the various solvers that you can swap in with Keras. So all the various things that will control how the models actually fit, other than the data. So the only thing that's not passed in there is the data. When you go to actually fit the model, you do classifier.fit. So this is consistent across all the dozens, probably dozens of classifiers. I don't know if they have 100 estimators in SciKit Learn. Maybe they do. But yeah, the idea is you instantiate the estimator, pass along any parameters here. These are called hyperparameters, and then you fit the model to the data. Okay, and that fit method returns the classifier itself. Once you've actually fit the model, classifier has like a bunch of useful attributes on it, like the coefficients that it learns. So this is the intercept, and this is the slope of the line. So that's the line that would be the best fit line for predicting the data here, X train and Y train. Okay, and then the prediction side. So we fit a model. We've done this part here. We've done training by instantiating the estimator, and then passing in the X and the Y to the fit. And then to do the second part here, the prediction and the evaluation, we will predict with classifier.predict. This is going to be a NumPy array of the, in this case, since we're classifying, it's going to be the discrete outputs, 1 and 0. And then the evaluation step here is done by, well, SciKit Learn has a bunch of useful helpers for that. You could do it manually and say, okay, what % of these did we get correct? That'd be the accuracy. So you can like manually do that with np.mean, or I would recommend using SciKit Learn's built-in .score method, and that'll call the appropriate evaluation function. There's different scores that you can come up with. We'll mostly focus on accuracy and standard error or regression. Okay, and then we can see the score on the test data set and the training data set, and we can see that there's a bit of a gap there. So we'll talk about why that might be later on. Okay, any questions on the API? Yeah, David.
So those coefficients that came out of the logistic regression, is that just that's the coefficients that actually you apply to X and then you feed it into the logistic function?
Right, so in this predict, maybe we can bring up, I'm not sure what the source code looks like. Let's see. It's probably not too useful. Yeah, not too useful. I can try and see the decision function. Basically what NumPy is doing, or SciKit Learn, maybe we can plot it here. So what SciKit Learn is doing is, for each of the, no, that's not what we want either.
That line there is not.
Yeah.
It's not the same slope and intercept.
Right, right.
You would plug in the slope and intercept that you got, and then solve for where the probability was 0.5.
Yep.
You need to derive that line.
Yeah, that's what it's doing. I don't know if this will be any helpful. So this is calling the dot product of, we can do this if we want. We have classifier.coef. You all are using Python 3.5 enough, right? Dot products, classifier x test. Are my dimensions right here? Let's see if it works. Nope. X test classifier. Oh no, this isn't gonna work because because I don't have an intercept in X test. That's bad. I could add an intercept. I'm going to skip it, but yeah, that's the basic idea. It's doing the prediction by doing that dot product. Yeah.
You've got two X's, right?
I have a train and a test. Yeah.
Oh, gotcha.
I just don't have
there's two columns there, but that's just on one. No, wait. Those are the data points. Those are.
What's that? Okay. Right. Classifier.intercept. If I really wanted to do it, I would have to.
All right. So yeah,
intercept separate.
There's
sorry.
3 parameters. Right?
Yes. Yeah. If I really wanted to do it, I would have to do some stacking of matrices, which probably
Don't go any further.
Cool. Anyway, what it's doing is we have the line, y equal mx plus b, right? In this case, it's y equal, intercept plus m1 x1 for this, plus m2, which is this, times x2. That gives you a y, which since we're doing logistic regression, after that we'll do the activation function, which is what deep learning people would call it. We would take the sigmoid of that. And then that would give us a number between 0 and 1. At that point, we'd cut it off. Anything above 0.5 would be a 0, I guess, and anything above it would be a 1. So. Cool. Yeah, coefficient intercept. Any other questions on that? So that's like the idea behind SciKit Learn. The nice thing about SciKit Learn is it has the consistent API so that you can just swap out different models, tune your hyperparameters as needed, and you should be good to go. So it's always instantiate the estimator, call fit with the x and the y, and then measure it with score, things like that. Yeah.
Is there like a supervisor you can put on top of it to essentially make like a quad tree, oct tree? And then for each box, like train a bunch of different models on it and see which one works best?
Let's see here. How would you be splitting?
Imagine that I have 2 rings, like donuts in 3D.
Mm-hmm.
And I'm either like on the surface of one of these donuts, or I'm in the middle of space, and that's not a donut. And it's like I can approximate this with like 2 circles, and then I have like a 3rd model in the middle for the linkage. And it's like you essentially break them into like a grid, in like n dimensions. And then for each box, you try to be like, okay, which model is predicting this best? And then you break that into like quarters or eighths or whatever.
Yeah, I think
until you get the tolerance that you want.
I think a stacking classifier would work there. Well, this is going to be merged into the main SciKit Learn soon. I think that might work for you. The only thing I don't know about is the splitting of the data based on the values themselves. That's the only thing I'm not sure about. But yeah, it's this meta classifier step that should work for you, if I'm understanding correctly. Maybe I'm not. But yeah, that might work. Okay. So just to show like another example here, K-Neighbors Classifier, we've done logistic regression for classification. Another example is K-Neighbors Classifier. So this has, I think, one important parameter, which is the number of neighbors to consider. So what this is going to do is going to say, for each point in the data, my prediction is going to be the closest label to me, if that makes sense. And we can visualize this one here. So, anywhere on this 2-dimensional grid, it's going to take like the Euclidean distance to the closest point. So like, and then the line here that we've drawn is kind of the boundary point between the two. So like this would be equidistant between like this point and this point. If that makes sense. And then, so since we've set the number of neighbors to be 1 here, this in neighbors here, it controls how many points in like in your area, your region to consider. And then the k closest points will get to vote on which one it thinks should be like the correct label. With n neighbors equals 1, it's going to be like super raggedy because it's going to be just considering only the influence of the one closest point. If you do like a bunch of points here, then it's going to be smooth line because you'll be averaging from the votes of more labels. Yeah.
This is an example of overfitting.
Yes, like this. So if you think about it, well, this is a fake data set, but in the real world, if you're predicting flowers, whatever, if you want to do the species example, it's pretty unlikely that nature happened to evolve a little spot here for 0 to be in just this right x1 and just this right x2. Nature's probably not going to do that. Most things probably aren't going to have like these weird non-linearities here. So it's much more likely that the true, like if the angel comes down and tells us the parameters, it's like actually a linear line here, and then there's some noise that's been thrown in there. So this is definitely overfitting.
Is there like one that basically you have a probability distribution over a point at whether it's A or B?
Yep. So you can actually get that with Canon.predictProb A. This will give you the well, that's a bad example. Let's do classifier.predictProb A. That one was all 0, 1 because of predictProb A x. So this gives the probability of each point, scientific notation. So for each value in x, train or x test, whatever, you get the probability of it being a 0 and then the probability of it being a 1. And then if you want to do like a, you could generate a grid here if you wanted.
So given a point, given these like actually output like a probability distribution function, and I can then multiply against something else.
You have a decision function, and then otherwise I would recommend using a Gaussian, SciKit Learn, Gaussian, mixture method. GMM. This might be about what you want, I'm guessing. This is a negative log likelihood, but you get the density function. So, and they do this by generating a mesh grid, I'm sure here. Mesh grid, yeah. So, and then do they manually do this? All right. Score samples, so that'll give you the probability at each point. Okay, we have an exercise. Play with different values of n neighbors and see how this training and test score changes. So specifically like the difference between the two. So yeah, give that 5 minutes. If you want 5 minutes, give it 2 minutes. And then if you want, you can uncomment this. And then up in the toolbar here, you can like insert cells above, where you press A and B to make new cells above or below. Yeah, so basically play around with the hyperparameter here, the number of neighbors, and then see how the training and the test scores adjust. There's train sub. Okay, we'll talk a bit about what they're doing here. Yeah. All right. They split their data set up into a third training set, a test set, and a validation set. We'll talk about that in a bit, but I don't know. The way I did it was made a bunch of classifiers, one for each number of neighbors from 1 to 19, I guess. And then for each of those, we fit the model to the X and the Y train data, and then we get the train score and then the test score, and then plot those. So what happened here? Oh, that's interesting. Did I do this backwards order? X test, Y test, test scores. That's strange. Typically, the training score will be above the test score. For whatever reason, it's kind of flipped here. Interesting. Once we get past a certain number of neighbors, so this would be like overfitting over here. We'll see a better example of this in a minute. Any questions on like the main API? How How's it going so far? Good. We'll go for like another 15 minutes, half hour. Depends on how people are feeling. Let me know. Like I can do whatever. Yeah, that's the main idea. Is you've got your x and your y for supervised machine learning anyway. You have an x and a y. You instantiate the model. You fit it, and then you evaluate it somehow. Measure the score. Okay. We'll jump into the next notebook here. This is
I just have a question. So since you're featuring the SciKit Learn API, have you also played with XGBoost?
a little bit, yeah.
So what's your impression of how easy to use the API?
Is it mostly compatible? I thought it was. I think so. I'm pretty sure they took the SciKit Learn Estimator API. I could be wrong, but yeah. Do you know? I'm like reasonably certain. Yeah, XGBoost. XGBoost is a distributed, or well, it can be run in distributed mode. I'm like almost certain that we don't want this. Yeah, XGBoost. If not, I'm sure there's a SciKit Learn wrapper. So. Matrix. Okay. So instead of using NumPy arrays, they do use these custom objects. But okay, so they call it train instead of fit. Predict. So. Okay, never mind. So it's not that compatible. Ha, I was wrong. I don't know why I thought it was.
Are there any sklearn libraries that take a model and like export them to your favorite language of choice, like JavaScript, like a JavaScript function?
No, I'm not aware of JavaScript.
There's like an output, not like there's a.
Yeah.
So it's like I could like embed that model in a web page and have it drive some business logic.
There are ways to.
There were like a Python preprint ASD if you could.
Yeah. That's more commonly what's done. So, well, typically, the most common one is just pickling the model. That pickles up everything that needs to be reloaded, and then you can like put a Flask wrapper or something in front of it, and then hit it, to do predictions. That's fairly common. There have been various attempts to serialize SciKit Learn models, and then load them like with Protobus or something. Like that's what Apple's CoreML does, is serialize SciKit Learn, or some SciKit Learn models with Google Protobus. Yeah, that's kind of a pain point though, I think, that a lot of companies deal with. But as far as serving it, yeah, nothing for JavaScript that I know of.
I mean, just
put a REST endpoint in front of the model. Yeah. I'm sure there are libraries that try to do that, but I'm not sure like a good one. My company sells an enterprise product, if that's something that interests you. And one of the things that you can do is put a REST API in front of a model. So if you have an enterprise, get in touch. Okay. Yeah, XGBoost is it's like super popular on Kaggle because it works really well. And you can run it distributed if you have very large data sets. So I'm almost certain that there's a SciKit Learn wrapper for XGBoost, and maybe that's what I've used in the past. Although SciKit Learn. Okay, so they have a class. Okay, XGB regressor that works apparently just like the SciKit Learn estimator.
So it's kind of compatible in one direction but not the other?
Yes, if I understand it right, then yeah. They implement SciKit Learn API, but not the other way around. Cool. Okay, so this is notebook, 6, regression. So we'll go through this one somewhat quickly, but the only thing that really changes here, instead of predicting, so in this case we have the x and then the outcome, the y, on the y-axis. This time y is it's numeric, it's continuous valued rather than discrete valued. Okay, linear regression, it's the simplest, probably simplest quantitative regression predictor. Let's see here. Oh, right. So yeah, this is a slightly annoying thing that you have to worry about with regression. Getting your so there's a difference between x. So what do we call this x? X is a one-dimensional array, and then x you can either reshape or new axis. Always make sure there's a difference between these two, basically. This is a one-dimensional array. This is a two-dimensional array with one column. So those are different according to SciKit Learn for good reasons, but yeah, it can be annoying if you ever get cryptic error messages about why that didn't work. Okay. Train test split, as usual. Test size 25%, train size is going to be 75%. And yeah, just like before, we're going to set up linear regression. There aren't very many parameters for this, just intercepts. Yeah, that's the big one. Normalize, which we will not do. You make your linear regression, and then you fit it to the data. So that's like, again, nice consistent API, even though we have a completely different task of regression now. Instead of classification, we have the same API, and then our attributes, and then to go to predicting, we can go ahead and do that. So this is, yeah, David's question earlier is much easier to demonstrate with linear regression because it is just a high school algebra at that point. So yeah. Okay, any questions on regression? It's nice when it's consistent, right? All right. Predict is the same, only now instead of giving you back like a 0 and a 1, it's going to give you back a continuous valued item. And you can see for regression, that is what regression does. It finds the best fit line, and then for each of these points, it's going to, right, for each of these x's along here, it's going to predict the point on the line. So that's what regression does. Okay, so this would be, so this might be an example of underfitting the data. So there's some sort of pattern in here that our simple model hasn't captured, and there's various ways of going about fixing underfitting. A way to check this is when so there's going to be a gap between the performance on the test data set and the validation data set, and you can either make your model more complex. So that based in regression, that basically amounts to adding more features. So like transforming the X somehow to better capture what's going on in the data. So making the model that you've selected more complex, or you can reach for a more complicated model. So going from something like linear regression to like k neighbors with a small number of neighbors, something like that. Okay. So we'll see an example of the first type is making your model more complex. So for this exercise, we're going to have two features now. First one is going to be the actual X that we generated up here with this, I think it was a lens base. So we're going to take this X and then we're going to enhance it somehow by also including the the sign of 4 times X into the model. So earlier we had a single predictor, and now we're going to have 2 predictors. We'll have the X, and then we'll have sign of 4X. One function that might be useful here is np.sign. Takes an array, returns array. Okay, so this is the feature that we're going to add, and then you might also want to look into np.concatenate. That takes an iterable of arrays to join along an axis. So take a few minutes to work on that. Let me know if you get stuck on the feature, the feature enhancement side. Yeah. So you see that they decided to do the concatenation twice, once for the train and once for the test. That's fine here. It is to take the original data, x train, concatenate that with 4 times the sign, or the sign and 4 times the original feature. And then axis equal 1, that's a numpy thing. Axis equals 0 is vertically, axis equals 1 is horizontally, and then this individual stuff passed there. And then you can see for this prediction, so again, once we've got the data transformed, the fit step is identical. We're just passing in the new data, the XX train, and then predicting for XX test. And you see that the orange dots here are the predictions, and those are quite a bit better now that we have this more complex model with these 2 features. The score is going to be higher. Questions on that? Bit of a NumPy exercise, one big thing. Okay, we can also do, swap out the model for k-neighbors regressor. This will have a single neighbor, and again, we can kind of plot these. In this case, it's going to be, it's always going to predict the closest point. This is going to be overfitting, right? Since it's impossible to get one wrong, right? For the training data, you're always going to predict your own point, which will always be correct. And it does an okay job for the test data set in orange here, 92%, which was better than the original regression model that we used, which was just the straight line here. Okay, yeah, so give this one a shot as well. Load the Boston housing data set, sklearn.datasets, imports Druid.sklearn. From sklearn.datasets, import load Boston. Boston equal to. This is a data set on housing prices in Boston, and then the data we call as the X. You can read about what the features are. 506 houses by 13 variables, and then the Boston.target is going to be the price of the home. I forget what the units are here. Yeah, so fit is for a k-neighbors regressor, and then linear regression for this data set. So give that a shot, and then just I don't know what all they do, but yeah, maybe just do like a train test splits, and then compare the score, and then we'll jump down to why you might want to do this train test split, which I've been avoiding thus far. for this one, train test split on the data, which is the x, and then the target, which is the y. Linear regression, we don't do any hyperparameters. We fit it to x train, y train. We look at the test score. This is an R squared now, which I think David mentioned last time. Can't remember. No. It's like it's a score. I don't know. It's flawed in many ways, but a higher number is better here. So the linear regression with just the default parameters does better than the k-neighbors regressor. We try n neighbors equal to 1 here. See how it does. Yeah, so not so good there. I don't know if they play with other parameters here, but in general, it looks like well. So if we do k and r dot fit, k and r dot score. If we look at the training data set, with n neighbors equal to 1, y train, it's going to be perfect. Even if we lower that, it's still probably going to be a bit higher. So, looks like the regression is going to be a bit better on this one as far as the R square goes in mind. Okay, so I think maybe this will be the last notebook that we go through. Jumping forward to the 13th notebook, so we're skipping a few here. But looking at cross-validation, so this is kind of talking about why we've been going through this train test split stuff and another way to deal with it. Let me make sure it's validation. CV. Yeah, so this idea is trying to deal with overfitting, where, I mean, you kind of saw it in the last notebook on regression, where, for this data set, when we had the k-neighbors regressor with a single neighbor, right? For any point on this, for any x, basically, it's going to look at the nearest point, and that's the only thing that's going to, the nearest xy point to it. That's the only thing that's going to determine what you're going to predict. So for any x along here, the predicted value is just going to be the closest one that's in your training data set. And that's, that can be problematic when you have some kind of noisy data, which is all data sets typically are going to have a bit of noise in them. And your model can end up overfitting it to just little bits of noise in the data. So like, the function we used to generate this was like a smooth sine curve. It doesn't have any of like the little noisy bits here that you can kind of see. The true data is just a smooth sine curve, but we've overfit it in certain places. Okay, so there's a few strategies for dealing with that. We've seen the train test, but yeah.
Which notebook is this?
13, cross-validation. So we've seen the train test split, which is like a basic way to, it's like a first approach to measure if you're overfitting. The way that shows up is the train score is high, while the test score is low. We saw that on the very last, the exercise at the end here, when we did k-neighbors regressor with n neighbors equal to 1. We got so for the train data set, we did perfectly, right? Since we're always going to predict the correct value with n neighbors equal to 1. But with the test data set, we did quite a bit worse because we're overfitting essentially. So that's this gap between the training and the test data set, the score on those, that's going to be a sign of overfitting when the train is much higher than the test score. So there's one way to kind of deal with this is a process called cross-validation. So you start out with your entire data set, and early on you might do a train test split like we've seen so far. So this part we've seen, and this is what helps us identify overfitting. But to actually kind of remedy it as you're fitting the model, what you can do is kind of do a bunch more train test splits on just your training data set. So down here, each one of these is just looking at the training data. We've set aside the test data completely now. And we're going to basically break it up into even smaller chunks. In this case, we're doing, it's called cross-validation. We're doing 5-fold cross-validation, where you split your data set, and for the first fold, you take the first, some 20% of it, and set it aside to evaluate your model on, and then you actually train it on the rest of the 80%. So again, this is, everything here is just the training data set, but within that training data set, we're breaking it into smaller chunks of actual train for the fitting, and then the validation, the test data set here. Okay, and we'll see in just a second, hopefully in just a second, we'll talk about what this helps out with, but it helps prevent overfitting. Okay. This is like manually doing cross-validation. Andreas and Alexander say this is easy. I don't know. If you're new to NumPy, this may be a bit dense. So I think we'll skip over the manual step and just say that this code here is implementing something like this, where you take, you basically fit your model 5 different times on various arrangements of your training data. And then we'll see a utility that SciKit Learn provides for us. Okay. So we've done like these, we split our training data set into 5 pieces, and like on the first piece we do 97%, the second chunk we do 90%, and we do perfect on these too, so there's a bit of variation there just baked into the data set, training data set, this various subsets of the training data set. Okay, so SciKit Learn gives us some utility functions to help out with it. So one of them is like cross-val score. And what this will do is it'll take a classifier that's already been fit. In this case, classifier was a, I think, K-neighbors classifier. We've already fit it, and then we pass in an X and a Y, and it'll do, I mean, you control it, but I think by default it does like 3-fold cross-validation. And it gives you back a list of scores on each of those subsets. So this kind of gives you an idea of the variability in your scoring, how your model's doing. There are variations on it, stratified cross-validation, which we'll skip. And go down to the end here, take a look at this exercise. 3-fold cross-validation without shuffling the data. We kind of saw this already, but go ahead and give it a shot. So in this case, I skipped over this. So the last little thing here is instead of doing cross-val score with the classifier, you can use this K-fold or stratified K-fold, these little helpers, where you pass in like the number of splits that you want, like 3, and this will give you an iterator for your data. So CV equal to that, and then CV.split, iris.data, iris.target. Sorry for skipping over this. Is a generator. X train, so train, test in, actually how I would write this is X train, Y train, X test, Y test. So an iterator, generator of tuples there. Print X train, I think this will work. Iris.data, iris.target. What did I mess up? Sorry. Test. Oh, my bad. Train, test, and this. Print train. Sorry. Yeah. Train.shape. Right. Yeah, sorry about that. X train. Yes, obviously. Sorry, I confused myself. Xtrain.shape. Yeah, this gives you iterators of, I don't know what I was thinking. These are iterators of XY pairs. Sorry about that. There's no test data set because we're doing cross-validation. My bad. Okay, so this is the way these little helper classes work, is they take care of shuffling and iterating over the data, breaking the data into various splits. If you want, maybe we'll skip the exercise. I don't know if you all are wanting to do that, but yeah, it's a two-liner. Yeah, you can feed that CV in there, or you can pass the integer 3, and it does the same sort of thing. So, okay, I think complexity. This one I'll run through it real quick. This is like the payoff, I guess, of all the stuff we talked about with like train test split and cross validation. It's hyperparameter tuning. So up until now, we've seen like, you know, when you pass in like the k-neighbors regressor, you have that number of neighbors to use. That's called a hyperparameter, since you specify it when you instantiate the model. So remember, SciKit Learn has the idea of you instantiate a model, so like you call linear regression or something, that class, to instantiate a model. And then at that time is when you specify all the hyperparameters, like whether you want an intercept or not, what the penalty should be, the loss function, all that is all hyperparameters. And then SciKit learns and goes and learns the regular parameters, like the coefficient and the intercept. Hyperparameters are where you can do a lot of work around overfitting and generalization, so that sort of thing. And this is like what the a bulk of SciKit Learn is built to handle, I guess. A bunch of SciKit Learn. So in this case, we've got 3 different examples of the same estimator. We're doing k-neighbors regressor to predict this y. And in the left pane, we have a low number of neighbors, so 2 neighbors. This would be an example of overfitting. Like you can see, the prediction line here is fairly jagged. The middle pane has 5 neighbors, and then the right pane is 20 neighbors, so it's much smoother. And you can kind of see like there's a sweet spot here where with 5 neighbors we get relatively close to the true function that generated this random data. So we know the true function. So this is like the ideal one in this case. Is you're getting close to the correct one. When you're fitting various models to your data set, you're going to be kind of looking for where your accuracy or whatever you're trying to measure tops out for your test data set. And then kind of the trick of SciKit Learn, machine learning in general, is to find this spot without tricking yourself, basically. The training data set, so if you're just doing like a naive thing of fitting, of measuring your performance on just a training data set, that's always going to be increasing in model complexity. That's what's on the x-axis here. So like in this example, this is a very complex model, just since like there's so many little twists and turns to it. This red line here is a complex model, we would say, compared to something like straight line is relatively simple. With like a single neighbor, you're going to be doing perfect, so you'll be over here in the corner here. But you don't generalize as well since you overfit. So this is a region where you're overfitting, and then this is a region where you're underfitting. This one graph kind of like summarizes the difficult part of machine learning, other than like the data wrangling part, which is more annoying than anything. Yeah. So the rest of this notebook here is like more of an advanced but necessary topic when you start to use machine learning to do whatever. It's something you'll run into is where your performance is good on the training data set, but it doesn't do as well as you would expect once you go to actually use it for real. So various utilities and stuff for dealing with that. I think we'll call it there just since it's getting a bit more advanced and a bit late, but yeah, if you're interested, check out the rest of this, let me know. Otherwise, you can check out the SciPy tutorial. The videos are online, and they probably do a better job of teaching it than I did. So yeah, any other questions there before we wrap up? Thoughts? Are people eager to apply it? if you have any issues, let me know. Happy to help out. But yeah, that's basically it. I think the key takeaway for this is the consistent API that SciKit Learn offers. So you instantiate your model and then you fit it on your data, and then predict and store and all that. And then everything else, like that takes like 5 minutes, right, to introduce. NumPy arrays and stuff if you're not familiar with those. But the actual API takes like 5 minutes to explain, and then most of the rest of the time we were talking about how to deal with this last notebook is how to deal with model complexity and overfitting. And that's actually the difficult part there. So keep that in mind. Cool. With that, I will let you all go. Are there any other wrap-up announcements?
Well, thank you, Tom.
Cool.
Thanks for coming in, rocking it.
No
Do it
problem.
again. Last month, I totally forgot to thank Pillar and Forge. Without them, we literally would not be here. We'd be somewhere else, but